Now we will move into the next topic that is called conditional probability. Let omega capital F capital P be a probability space. We are not making any assumption over this probability space. If A comma B belonging to F, both are events with the P of A is greater than 0. That means it is not a impossible event. Impossible event means the probability with that event is equal to 0, and sure event means the probability of that event is equal to 1. Rare event means the probability of that event is open interval between 0 to 1. So here it is a non-impossible event. Then the probability of the event B under the condition the event A, that is defined as P of event B slash event A, that is same as P of A intersection B divided by P of A. This is well defined because the probability of A is strictly greater than 0. So this conditional probability is going to be probability of B given A is same as probability of A intersection B divided by probability of A. This is called the conditional probability of event B given event A. Few properties on the conditional probability, but before that let me give the definition of independent events, then I will come to the results on the conditional probability. The first definition: two events A and B are said to be independent if and only if the intersection probability is same as the product of the individual probabilities. It is a if and only if condition. Whenever this condition is satisfied by any two events, then we call it as both the events are independent. If two events are independent, then this condition will be satisfied. Based on this, I am going to give two definitions. One is called pairwise independent, the other one is called mutually independent. The next definition, that is a pairwise independent events. A sequence of events AI, where I is equal to 1, 2, so on, is said to be pairwise independent if you take any two events that satisfies the independent property, that is P of AI intersection AJ, that is same as P of AI into P of AJ for all I is not equal to J. So if you take any two events that satisfies the independent condition, then we conclude this sequence of events or this collection of events are called pairwise independent if it satisfies the independent condition. The next definition, that is mutually independent events. A sequence of events AIs is said to be mutually independent if and only if for any finite subcollection, that is A1, A2, so on, AK, the probability of A1 intersection A2 and so on intersection AK, that is same as P of A1 multiplied by P of A2 and so on, P of AK for all K. That is very important. That means if you take K is equal to 2, so if you take any two events in this collection, that satisfies the independent property or independent condition, or if you take any three events, that also satisfies the independent condition. Like that, if you take all the possible number of events, that is a subcollection, from that collection of events satisfies the independent property, then we conclude they are mutually independent events. Sometimes we won't use the word mutually. If you say that a few events are independent, that means by default they are mutually independent events. You see the previous definition, that is a pairwise independent events, but that is satisfied only for any two events, not 3 or 4 or 5 independent properties not going to be satisfied. That means the mutually independent events implies they are pairwise independent, but the pairwise independent event need not imply the mutually independent events for the collection of events. So let's go for one simple example for pairwise independent and mutually independent, then we will move into the properties on the conditional probability. So the example, as follows: let omega consisting of 1, 2, 3, 4, let A be the event consisting of only two elements, 1 and 2. Similarly, P is the element consisting of 1 and 3, and C is the element consisting of 1 and 4. And we assume that probability of singleton element W, that is equal to 1 divided by 4 for W is equal to either 1 or 2 or 3 or 4. Now we will verify whether these events satisfies the pairwise independent as well as mutually independent, or only it satisfies pairwise independent, not the mutually independent. Let's go for finding A intersection B. That is nothing but the sample 1. And similarly, if you go for A intersection C, that is also singleton element 1. If you go for B and C, that is also singleton element 1. If you go for A intersection B intersection C, that is also singleton element 1. Whereas if you compute the P of A, that is 2 by 4, that is 1 by 2, and P of B, that is also 2 by 4, that is 1 by 2, and P of C, that is also again 2 by 4, that is 1 by 2. Now if you compute P of A intersection B, that is going to be 1 by 4. Similarly, if you compute B of A intersection C, that is also 1 by 4. Similarly, P of B intersection C, that is also 1 by 4. Whereas P of A intersection B intersection C, that is also 1 by 4. For example, if you test P of A into P of B into P of C, that is going to be 1 by 2 into 1 by 2 into 1 by 2, that is 1 by 8, which is not same as a P of A intersection B intersection C. Whereas if you go for P of A intersection B, that is same as 1 by 4, that is same as P of A into P of B. Similarly, probability of A intersection C, that is same as P of A into P of C. Similarly, P of B intersection C, that is same as P of B into P of C. That means it satisfies the independent condition for any two events, not for all three events. That means in this example, A, B and C are pairwise independent events, but they are not mutually independent events, because it does not satisfy the independent property for three events. So this is a very simple example. Conclude pairwise does not imply the mutually independent events in general. Now let us go for some properties on conditional probability. Some important properties on conditional probability. The first one, so before that we have a probability space. Let omega capital F P be a probability space. In that probability space we are going to give the properties. The first one, P of the conditional probability, that is a probability measure. The conditional probability, that is also a probability measure over omega, condition on the event A. That means it satisfies the axiomatic properties of the probability, that is the three properties. P of A's are always greater than or equal to 0 for all A belonging to F, and P of P of a whole set is 1, and mutually disjoint events P of union is same as a summation of a P of A's. The same thing here also is satisfied. Here the P of A given A, that is going to be 1, whereas in the axiomatic definition of probability the P of omega is 1. Here the conditional probability, that is also probability space, here P of A given A, that is equal to 1. Second important property, that is if A intersection B is empty set, then the conditional probability of event B given A, that is going to be, because this is same as a probability of B intersection A divided by probability of A. since A intersection B is empty set, P of empty set is 0, therefore probability of B given A, that is equal to 0. Third result or third property, P of B intersection C given A that is same as the conditional probability of event B given A intersection C multiplied by P of event C given A. If the probability of A intersection C is greater than 0. Whenever you want to compute probability of B intersection C given A, that can be computed in the form of a probability of B given A intersection C multiplied by P of that is multiplied by probability of event C given A whenever probability of A intersection C is greater than 0. The next result related to the conditional probability, if A1, A2 and so on, n events belonging to F with probability of A1 intersection A2 intersection an minus 1, if that probability is strictly greater than 0, then one can define probability of intersection of n events. The assumption is intersection of n minus 1 events probability is greater than 0. We have n events belonging to F. Then one can find the probability of intersection of n event is same as probability of A1 multiplied by probability of A2 given A1 multiplied by probability of A3 given A1 intersection A2 multiplied by the same way the last element is a probability of an given A1 intersection A2 intersection so on intersection an minus 1. This is possible whenever you have a n events and the probability of intersection of n events provided probability of intersection of n minus 1 events is greater than 0, one can always find the product of conditional probability with the intersection of events. This is valid for any countable number of events satisfying these conditions. There is no assumption over the events to apply this result. Now, suppose these events are mutually independent or mutually independent events, then the results are going to be simplified as follows. That means suppose A1, A2, An are mutually independent events, all are belonging to F. Suppose these events are mutually independent events belonging to F, then the P of A1 intersection A2 intersection and so on An, that is same as, we are retaining the other condition, intersection of P of A n minus 1 events, that's probability is greater than 0, we are keeping that in. P of A1 intersection A2 intersection An, that is same as, you see the previous one, first one is P of A1, the second one P of A2 given A1. Since A1 and A2 Ans are mutually independent events, the intersection, the conditional probability A2 given A1 that is going to be a probability of only A2. Therefore, this is going to be probability of A2. Similarly, probability of A2 given A1 intersection A2, that is again going to be probability of A3, and so on. The last one, it is P of A. That means if events are mutually independent, then the intersection probability is the same as the product of individual probabilities. So this can be proved also. So I am just using that result.